AP Statistics, Unit 1, Topic number 4, covering the summarization of numerical data. So here we did a brief computation of measures of central tendency, mean and median, measures of spread, range, standard deviation, and then measures of position, which we didn't get to finish, hence the video. In 5th period, I was able to cover standardized scores, and standardized scores, also known as z-scores, basically scale any data value and change its it scales its deviation away from the mean by a standard deviation. So it's going to take the deviation in x bar, and then it's going to divide by the standard deviation, so it standardizes the value. So then we talk in terms of standard deviation. So for example, in letter D, the 9-minute travel time was let's see here, I forget what it was. I think I skipped a step and I gave the final answer. So the 9 minus 21.73, I'm going to do it in a calculator really quick. This was negative 12.73. And that's going to get divided by 9.45, which was the standard deviation for that problem. And when you divide, you end up getting negative 1.347-ish. All right, so, and I had it there already underlined underneath. So basically what it's doing is it's taking how far away this value was away from the average, and even then, how far away from the average is kind of not a good objective measurement. So what we do is we scale it relative to the standard deviation. So what does that look like with respect to one standard deviation, one average error value away? So then your units now are in standard deviations. Technically, you can think of them as unitless, but what we're doing is we're scaling them by standard deviations. So you can also think of this as the units being one standard deviation. So it's like using the standard deviation as a ruler. And then this means that this was over one standard deviation below what was expected, the expected being the average. So a 9-minute travel time is over a standard deviation less, or over a standard deviation lower than the average travel time for these residents of San Antonio and how long they take to get to work. So that's a lucky person. Okay, so percentiles, we also started the discussion for percentiles in both classes, one on the day, the other one on the next class day, the next synchronous class day. So I had to cover it right before we started talking about the next situation, because the next situation covered other percentiles, 25th and 75th percentiles. So that's Q1 and Q3. So those were introduced in the next handout. So we kind of have an idea of what percentiles are about. So what we're doing is we're calculating what exact percentile a data value falls in. So see, this 14-minute travel time, if you remember, if we were in class and we did that, 7th period, I don't think we got that far. But the idea was this. You look at the data set, and that 14 was here. There were 4 values before that 4. So then you divide 4 out of the whole, which is 15, and that's the percentage before the 14. And in that case, that was, I forget what it was. It was about 27%. It was a little under 27%. So we say that that particular person is in the 27th percentile. It's actually probably more accurate to say the 26th percentile. But give or take a percent, it's not going to be a big deal. We do the same thing for the travel time of 41 minutes, which if you remember, that's the last value in that 14 data set. So there are 15 value data set. So that means there are 14 values lower than that 41 value. So to find out what the percentile is, the percentage would be the 14 out of the 15. And this is going to equal to, if you put it in your calculator, 0.9333, and the threes go on forever. So it's a repeating decimal. So 9.33333 and keeps on going. So then we will go ahead and respond. The person or the San Antonio resident with a travel time. It's a work travel time, but I'll just put travel time. Of 41 minutes is in the 93rd, we'll say, percentile. And the idea here, 93rd percentile is one of the largest, or that is the largest value in this data set. So that's pretty large, 93rd percentile. So you want to think, is this one of those situations where I'd want to be in the highest percentile possible? Or is this flipped? Is this a situation where I want to be in the lowest percentile possible? If we're talking about how long it takes for us to drive to work, ideally, you want to be in the lower half. This person's in the upper extreme. So this is an undesirable situation. Whereas, let's say, for example, if this were a test score, then yeah, you'd want to be in the higher percentiles. So you got to be mindful of what variables you're working with. And that's what these types of problems are going to be dealing with, numbers 2 and 3. So interpretations of these values are arguing based off of given values. So we'll look at number 2 and number 3, which gives us a little bit of practice with this stuff. So I'll start with number 2. Jenny earned an 86% on her first pre-calculus test. The class average and standard deviation were 80% and 6% respectively. So class average, X bar. Standard deviation, S. Two very common symbols we're going to be using a lot later on. So X bar and S. So the average student scored an 80%, give or take 6 points. So you can think of it this way. The average student scored anywhere between a 74%, I'm struggling to write a percentage symbol, and 86%. So the average student was anywhere between a 74 and an 86. That's what that means. The 6% standard deviation is a give or take. That's the average distance away from the mean that the typical student was or fell with respect to the mean. So the day after receiving her pre-calculus test result of 86, Jenny also found out she earned an 82 in her physics test. So disappointed at first. She then found out that the physics test scores, had a mean, so there's a bit of a typo there. Had a mean, or maybe I think had's fine. With is not. So had a mean of 76% and a standard deviation of 4%. So then the typical student in this physics class scored anywhere from a 72% to a, an 80%. So the typical student in this class, 72% to 80%, so that's 76, give or take 4. On which test did Jenny perform better relative to the rest of her class? So it's kind of tough to see at first. But if you look at those intervals that I gave, so those intervals I was giving just to, for instructional purposes, just to show you what the use is of having both the mean and the standard deviation. But now if you have those intervals and you understand exactly what those interpretations are or why or what the relevance is to those intervals, you kind of already have an argument here. You can hopefully see that the 82 lies to the outside on the right of that interval of the typical student, whereas our 86 is inside the interval for pre-calculus. So we can already argue that I think she did better relative to the rest of her class on her physics test, because she's above the typical student here. For her pre-cal, she's one of the typical students. She's inside the interval for typical average students. For physics, she's actually outside to the right of the interval of typical average students. And hopefully that makes sense. But we're going to go ahead and give a better argument than that. So here's my argument. So if that's the case, if we're comparing where she lied with respect to the mean in terms of standard deviations, I'm expecting she's going to have a higher standardized score for physics than she does for pre-cal. So I'm going to do this for both. So her z-score for pre-cal. And that's going to tell me how many standard deviations she was away from the average. She was above average on both, which is good. Let's look at our formula for a z-score. It's the observed x value minus the expected, which is the average. So what the person scored minus the average score, and then you divide by the standard score. So S. So in this case, for pre-cal, 86 minus an average of 80. Minus an average of 80, all divided by 6. So she was 6 points above the mean. 6 was the standard error, or the standard deviation. Therefore, she scored exactly 1 standard deviation above the mean. 6 divided by 6 is 1. She was precisely a standard deviation above the mean. So she's on that edge of typical student versus higher than typical student. Physics. So z-score for physics. She scored an 82. Average was a 76. Standard deviation was a 4. So 82 minus 76, I believe that's 6 points above the mean. But the standard score was a 4. Or the standard error was a 4. 6 over 4 is 1.5, if I do that correctly. So she's a 1.5 standard deviations above the mean in this case. So clearly, she did better on her physics test relative to the rest of the class. So once we scale it for how the rest of the class did, then she did better than the rest of the class in this respect. So she was further away from average with respect to standard deviation. So scaled relative to the standard deviation. So she scored higher in her physics course. Relative to her peers. And that's the idea of arguing using standard scores, standard deviations, or z-scores, because those are z-scores. And the symbol that we use, of course, for those are z, which is why we call them z-scores instead of standardized scores for short. So z is very short. Number 3. Pablo was given a summary sheet when his graded AP Spanish language quiz was returned to him. The summary sheet included his actual score, which was an 87, the class mean, a 75%, and his standardized score. Find and interpret the standard deviation score on the Spanish quiz. So they're going to vary it a little bit. So they told you his actual score, I'm going to call it X, is 87%. The mean score, we call that X bar, 75%. His standardized score, Z, which they told us flat out, 1.25, which he was above the mean, which is good, and over a standard deviation above the mean. It's good. Find and interpret the standard deviation for his score. So we want to know the standard deviation S. That's what is unknown. So I write down what's given, and then I also figure out what's unknown and what they want me to figure out. So it's also good for physics. So it's good for any other type of problem where there's a bunch of variables involved. You write down what you know, and then you also, in question mark form, write down what it is you need to know and what they're asking for. There's a formula that relates all 4 of these things. Z equals X minus X bar over S, which I plug in what I know. This implies, and I put a little implication arrow, this implies that 1.25 is equal to 87 minus 75 over an unknown quantity S. Now we have a algebra problem. This is an algebra 1 problem. You can solve by cross multiplication. Well, first off, that 87 over 75. 87 over 75 is what, 12? Over S is equal to 1.25, which I'm copying down the 1.25 again. That's an S, not a 5. I probably made it look more like 5. I don't know. But 87 and 75, I'm just double checking. That's 12. Okay, so then I have to solve for S. So then you divide 12. So S is equal to 12 divided by 1.25. So that for sure. So I'm going to take out a calculator. 12 divided by 1.25. 9.6. So then this tells me that the standard deviation was 9.6, and I have to interpret it. So I did the math here on this side. I'll do the interpretation on this side. So then, the typical, I'll use the word typical student scored within, this is a distance, it's an error margin, so it's like a margin. So the typical student scored within 9.6 percentage points from the average of, what was the average? 75%. So really we had students who scored anywhere between 65.4% and 74.6%. is basically what's going on. So the typical student scored within 9.6 points from the average of 75%. So it's an error window away from the average. It's the expected error from the average, or the typical error away from the average. And that's going to be it for this particular handout. That's all we needed to see that we hadn't finished yet.